Hi, everyone. So I'm very grateful to the organizers for having this chance to speak here. So I'm Ningchen Sun from UCAS and AOC in China. And the title of my talk is Probing the Dynamical Universe with the SiTian project. So this is the outline of my talk. I will introduce the scientific background and the concept of the SiTian project, and then describe some of the recent progress, and finally is the summary and opportunities for collaboration. So we know that we have entered a new era of time domain astronomy. So the time domain surveys make a movie of the dynamical universe in order to study how the astronomical objects change with time. Over the past decades, we have seen many time domain surveys, such as the Marshall and Ogle surveys dating back to the 1990s, and currently the Assassin, Pan-STARRS, and the ZTF surveys. And in the very near future, we shall have the LSST in the southern hemisphere and the WFST in the northern hemisphere. So the time domain surveys have increasing discovery capabilities, and they will reveal the new objects and new phenomena in astronomy with which we can probe the new physics that can't be studied in Earth laboratories. So astronomers have made significant progress in the field of time domain astronomy. So one example is the gravitational waves. So the LIGO, Virgo, and the Kagra observatories have detected many gravitational waves. So that's opening a new window for astronomical research. For one event, the GW170817, astronomers have also detected its electromagnetic counterpart. So even with this single object, astronomers have answered a lot of long-standing questions, such as the origin of short gamma ray bursts, the origin of heavy elements, and the equation of state of neutron stars. However, the optical counterpart of GW170817 was identified at more than 10 hours after the GW signal. So very unfortunately, astronomers missed the very early light curve of the associated kilonova emission. And this early light curve contains critical information about the central engine of the gravitational event. So the lack of early light curve prohibits discriminating different models with different merger products of this GW event. Another famous achievement in time domain astronomy is the usage of type 1a supernovae to measure the rate of cosmic expansion. So this is because the type 1a supernovae peak brightness and decline rate follows a very tight Phillips relation. So they can be used as standard candles to measure the distances of remote galaxies. However, till today, people don't really understand whether type 1a supernovae arise from the merger of two white dwarfs or a single white dwarf accreting material from a non-degenerate companion. Therefore, the origin of the Phillips relation is actually still unclear, and it is difficult to further reduce the intrinsic scatter of the Phillips relation. Theorists propose that the early light curve during the first few days of type 1a supernovae are very sensitive to their binary companions. So the early light curve can be used to distinguish the progenitor channels. But observationally, it is very difficult to capture this early phase. So from the above discussion, we see that the early stage of astronomical transients contains a lot of important information, but it's very difficult to observe them. This is because the current time domain surveys are either too slow or too shallow, or they have too small sky coverage. And on timescales shorter than 1 day, there are many astronomical transients which involves very fast. In order to explore this part of the discovery space of transients, we need a new time domain survey with a high cadence, with a deep detection limit, a large sky coverage, and very importantly, rapid identification, classification, and follow-up observations of the new transients. And that's why the SiTian project was proposed. The SiTian project will use a large array of tens of 1 meter class telescopes to monitor the dynamical universe on high cadence. So each telescope will have a large field of view of 5 by 5 square degrees, and in each node, 3 telescopes will point to the same sky area in 3 different filters. The final SiTian array will contain more than 18 nodes which will be able to scan 10,000 square degrees every 30 minutes in 3 filters down to a limit of more than 21 magnitude. And this slide compares the telescope field of view, the cadence, the detection limit, and sky coverage of the SiTian project, along with the other time domain surveys. So we see that compared with ZTF or LSST, the cadence of the SiTian survey will be at least 2 orders of magnitude higher, and therefore it will be able to probe the faster transients and the early stage of the astronomical transients. It will also have a deep detection limit and a large sky coverage, so it will be able to probe a large volume of the universe to search for transients. And this slide shows the whole picture of the SiTian project. The SiTian Brain is an intelligent control system which will automatically plan observations, operate the telescopes, and it will also take care of data management and processing and identify transients from the SiTian array, send alerts to the classification network composed of several 1 meter to 6 meter telescopes, and then arrange follow-up observations for telescopes distributed worldwide. So with the SiTian project, we can address many important questions in time domain astronomy, such as the explosive transients of gravitational waves, supernovae, tidal disruption events, and gamma ray bursts. It will also be important in the study of variable stars, stellar activity, exoplanets, and near-Earth objects. And in particular, because the SiTian project will have a very high cadence, it will capture the astronomical transients within the first 30 minutes. As we have already discussed earlier, the early light curves will be critical to distinguish some of the important models for these transients. We estimate that the SiTian project will be able to probe at least 1 or maybe as many as hundreds of kilonovae per year, depending on the assumptions. And for the type 1a supernovae, the SiTian project will probe thousands of type 1a supernovae each year. So the SiTian consortium now contains more than 100 researchers from more than 20 institutes and universities. We have also formed several hardware and software working groups and science preparation groups, and myself is leading the supernova working group. So we also have made significant progress since 2018. Last year, we have made a mini SiTian array for technical justification and training. And this year, we completed a SiTian prototype telescope located in Xinlong Station, which is not very far from Beijing. And next year, we shall have the first SiTian node at Lenghu Station, which have very good observing conditions. And several other telescopes will also be built along with the SiTian telescope, and they are funded by different universities. We aim at a national mega project with a budget of 1.5 billion Chinese yuan around the year of 2025 or 2030. So next, let me describe some of the recent progress. So as I mentioned, we have made a mini SiTian array, and this array has 3 telescopes, which each has a diameter of 30 centimeter and a field of view of 2 by 1.4 square degrees. And the mini SiTian array is used to justify some of the key technologies and to train the young scientists. And this slide shows the installation and operation of the mini SiTian array, as well as some images taken by the telescopes. So in a 5-minute exposure, the telescopes can reach a detection limit of 19.5 or 19 magnitude in the G and R bands. So during the last observing semester, the mini SiTian array has observed more than 1,000 hours, including 3 galactic fields, 15 supernovae, 20 gravitational wave events, and so on. So the right-hand panel shows the line curves of several variable stars in the observed fields.
2 minutes.
So okay, I will speed up. So the prototype telescope has a diameter of 1 meter and a large field of view. It is a modified Schmidt-type telescope. And currently, the camera mosaic is being tested and optimized and will be installed by the end of this year. And this slide shows the installation of this telescope and some of the images and light curves acquired by this telescope. And for the SiTian Brain, various components is also actively being developed and integrated, including observation planning, data storage system, and the data processing system. We can now report alerts for transients in 3 minutes, and we can achieve very good accuracy for astrometry and photometry. So in summary, the SiTian project will probe the dynamical universe on a cadence of 30 minutes, and this is 2 orders of magnitudes higher than current deep time domain surveys like ZTF or SST, and then we are making progress aiming at a national mega project. So the SiTian project will serve as an important component of the Beijing flagship project, and we are looking forward to collaboration among the BRICS countries. So by setting new nodes in the BRICS countries, we can make a global SiTian array which can monitor the full sky 24 hours a day. And we can also have a more extensive classification and follow-up network with the telescopes. We also welcome various components to be integrated into the SiTian Brain, like the alert brokers and the light curve classifiers. And we also look forward to carry out science research projects, and we welcome international postdocs and students. So if you are interested, please feel free to contact the project PI Zifeng Liu or myself, and I'm taking care of the international collaboration. So my talk stops here, and thank you very much.